what about infinite hypothesis spaces, right? And as I mentioned, infinite hypothesis spaces are not exactly rare, right? Anytime that you have real numbers, at your input, you're in an infinite hypothesis space, right? At least potentially, depending on the exact language, right? But even just a simple hyperplane is already an infinite hypothesis space, right? And you see that, if you just naively apply the formula that you have here, you're hosed. You need infinite examples. But somehow this can't be right? I mean, if you're fitting, a single layer perceptron that's just a hyperplane, you should need fewer examples, right, than if you're fitting a multi-layer perceptron which can form any, arbitrarily complicated frontier, right? So how do we do that, right? This seems like a very, big puzzle, right? Until you marry the APAC learning idea with this idea of the Vapnik-Chervonenkis dimension, which actually predates PAC learning by many years. This was invented in the late 60s by Vapnik and Chervonenkis, who it's named after. And then I think it was David Hausler who had this brilliant idea of combining VC dimension with PAC learning, right? So let's see what VC dimension is and then what it does for us, okay? And fair warning, VC dimension is one of those notions that, it's a little abstruse at first. It's like recursion. But then once you get your head around it, right, it just becomes part of your toolkit. Okay? So let me first of all just give you the intuition about what we're going to try to do here. And then I'll try to, step by step, see what the VC dimension is. And then finally we will have a nice, so the whole purpose of what we're going to do here is to then have a theorem, something like this, but where instead of the size of H, we're going to have the VC dimension. And then the hypothesis space could be infinite. As long as the VC dimension is finite, we're good. We can still, have a bound on the number of examples that we need. Okay? So this is the purpose of the VC dimension. And the VC dimension is really a combinatorial parameter. It says something about the hypothesis space. So, but first of all, let me give you just a very basic intuition. And the intuition is the following, right? So let's suppose that, I have some positive examples here, right? And some negative examples here, right? And now if you think about it, right, there's an infinity of frontiers that will separate these two, right? So there's actually a hyperplane in this case that separates the two, right? In fact, there's a whole bunch of hyperplanes, right, if you swing this around, right? But then there's also a lot of curves, right? In fact, the whole problem here is that we have two infinities here, right? One is the infinity of hyperplanes, and the second one is, say, the infinity of all curves, which includes the first one, and one infinity is larger than the other, right? But, this is all starting to sound very esoteric, right? The key is to focus on what we care about here, which is, we don't care about the details of these curves, right? We couldn't care less, at least as far as the training data is concerned, as far as fitting the training data goes, of whether we use this curve or this curve, right? Every single curve that I drew here, and let me draw some more to make the point even more clearly, right? And make some of them actually pretty bad, right? As far as separating the positive from the negative examples, which is what we care about for classification, right? These curves are all the same, right? So the bottom line is, I shouldn't care, or I shouldn't have to worry about the details of my frontier, right? What I care about is how it separates the positive and negative examples, and more importantly, whether it has the ability to separate the positive and negative examples, right? So there's a big difference between two hypothesis classes. For example, if this is my training set, there is no big difference between hyperplanes and other curves because they can both separate the training data perfectly, right? So in some sense here, you actually don't care. If you are in a situation, for example, where now there's a positive example here and another one here, right? Now this is a big difference between the hyperplanes and the others, because with hyperplanes you can't solve this problem. But with arbitrary curves, well, sure, you can still solve it. Okay? So what the VC dimension very cleverly captures is this fact that, sure, there's an infinity of curves, but we're going to bypass that infinity. We're only going to worry about how well you can classify specific training points, which are going to be finite. Right? This is the key, is that my data points are finite. I never have an infinite training set. And this is how we're going to keep things finite, is just by worrying about how you can classify the training set and whether I can find the curve that fits that splits those examples are not in my hypothesis space. Okay? So this is the rough intuition. So now let's look at what VC dimension is, right? And we're going to do this in one step at a time. So first of all, we're going to define these two notions of dichotomy and shattering. A dichotomy of a set is just a partition of the set into two disjoint subsets. A dichotomy of a set is what we do when we label some of the points positive and some of the points negative. Okay? That's what a dichotomy is. Right? And so in some sense, what we're trying to do here is form dichotomies, right? The classifier for a two-class problem, which is all we're going to worry about here, right, is just, it's a dichotomy. Okay? So that's a dichotomy. And now, what is the notion of shattering? Shattering is a relationship between a set of instances and a hypothesis space. We say that a hypothesis space H shatters a training set S if and only if, for every dichotomy of S, meaning for every different possible way of labeling the points in S positive or negative. I could label them all positive, all negative, these positive and those negative, or, these positive, those negative, right? These are all the possible dichotomies, right? And I say that the hypothesis space shatters that set of instances for every single dichotomy. There exists a hypothesis in H that is consistent with the dichotomy. Okay? The way to think about this from the point of view of classification, right, is that H is the hypothesis space of my classifier, right? And I say that H shatters my training set if no matter how you label the training set, there's always a hypothesis that gets those labels right. Okay? Questions about this? Okay, very good. So now we can define VC dimension. Well, actually, before we define VC dimension, let's look at an example of shattering. Okay? Here's the example, but let's do it one at a time. One piece at a time. So here are three instances. Okay? So what are the possible dichotomies of these instances? Right? Well, one is I label them all negative, right? Another one is I say label this one positive and these two ones negative, right? And I can, or then I can label this one positive and, these two negative, right? And so on and so forth, right? And so, what kind of hypothesis space would shatter this set of instances, right? It has to be a hypothesis space that allows me to separate the positives from the negatives no matter what happens, right? No matter how I've labeled them, okay? So what would that be? Well, let's see. First of all, too much. First of all, let's suppose that I label them all negative, right? They're all negative, right? Then, for example, if my concept is this, right? So I'm gonna use the convention that I'm gonna draw a curve, right? And inside the curve, right, is where it's positive, and outside the curve it's where it's negative, right? And what I'm gonna show you is that the set of ellipses, or even just of circles, is enough to shatter these instances, right? You see what I'm trying to do here? Okay, so first of all, what if they're all labeled negative, right? Is there a circle that's, a circle on the plane that does that? Well, sure. I just put the circle far away from all the instances and life is good, okay? What if I label them all positive? Where does my circle need to go?
It needs to surround all three of them.
Yeah, it needs to go around all of them, right? They need to all be inside it, right? Easy street, right? Well, now let's suppose that I've labeled, this guy positive and the other two negative, right? Where does my circle need to go?
The top one.
Yeah, just around this guy, okay? And right, you see where this is going, right? And now let's suppose that I say label these two guys positive and this guy negative. Where does my circle need to go? Let's go to ellipses because it's easy to draw. Although a circle would work here, right? Where does the ellipse need to go? Around these two guys, right? So if you look at the sum total of all these possibilities, right? What you get is this. Okay. So here are my 3 points, and here are all the ellipses I ever need to use to to reproduce any dichotomy of those points. Okay. So the conclusion is that yes, the set of ellipses on the plane, right, does shatter, or at least does shatter this particular set of 3 instances. This is what we've seen so far. Okay. All right. So this is an example of dichotomy and of shattering, and now we're ready for the definition of VC dimension. So what is the VC dimension of a hypothesis space, right? Let me first just say it to you, and then we'll kind of see what it means, right? So I have a hypothesis space, H, and I have an instance space, X, right? And the VC dimension, VC of H, of the hypothesis space H, is the size of the largest finite subset of H, that is, of X, that is shattered by H. Okay? If I can shatter arbitrary large sets, then the VC dimension is infinite. Right? I mean, if your concept class is very powerful, it can shatter anything, and the VC dimension is infinite. But of course, the interesting case is when the VC dimension is finite. Okay? So, how would you go about figuring out what the VC dimension of a particular hypothesis space is with respect to a particular set of instances? Well, notice the following. This is the size of the largest finite subset, meaning any subset will do, right? That is shattered by H, meaning that this has to work for every dichotomy. Right? So one way to look at this is as a game between you and an adversary. You are trying to make the VC dimension as high as possible. The adversary is trying to make the VC dimension as low as possible. Right? And you get to pick the set of instances. Right? Let's say that that the instance space was this room, right? You say like, okay, I'm going to start by picking by putting one instance right here. Right? And then, of course, one instance is anything can shatter one instance, right? But, start with one, right? And then your adversary says like, oh, I'm deviously going to label this instance, in order to make life hard for your hypothesis class. Okay? By saying, let's say that now I have, 3 or 4 instances, right? Now, you say like, okay, I'm going to put one instance here, one there, one there, one there. Okay, over to you. Another adversary goes like, I'm going to label this one positive, negative, negative, positive. Can you shatter? Can you reproduce that dichotomy? Okay? And so we keep on doing this until we get to a number of instances where no matter how you pick the instances, your adversary can always pick a labeling of them that there's no hypothesis that will be able to reproduce them. Okay? This is a little bit of a mouthful, so here's an example.